Hi everyone, I'm Anna Maria Mesaros. I'm one of the coordinators of the DCASE challenge. I'm happy to welcome you this year's virtual workshop, and even though we don't get to meet in person this year, I hope that we can have some fruitful discussion during these workshop days. So I'm opening this presentation of the challenge tasks by reminding you the main scope of this challenge. So we want to provide open data and encourage reproducible research. We want to attract new researchers to the given topics and to advance the research in the field of environmental sound analysis through repeated reference points and comparisons. The number of participants continues to increase. So this year we received a record number of entries. We had 473 systems from 138 teams. Of course, we also had a higher number of tasks than previously, so this might be one of the things. It was not announced in advance, but with the amazing support from the DCASE workshop organizers, we are able to give this year also a reproducible system award and a judges award for each task. I want to thank the task organizers for their hard work in preparing the tasks and the results, and then later participating in the review process for these awards. And I also want to thank the DCASE workshop organizers for providing us with this opportunity. All the awards from the workshop and the challenge will be announced at the same time. So I think that this is scheduled for the last day, but please check the latest technical program to make sure that you do not miss it. So now we will have the very short reports on the 6 tasks of this year, and I will present the highlights of task 1, acoustic scene classification. Acoustic scene classification means classifying a test audio recording into one of the given predefined acoustic scene classes. So we had 2 subtasks this year. One had 10 classes and then another one had 3. The first subtask was acoustic scene classification with multiple devices. And so the very special thing in it was that the dataset contained 15 different devices. 4 of them were real devices like we had in the previous years, and 11 of them were simulated using real impulse responses of various mobile devices. And then also some of them were not available at all in the development data. Then in subtask B, the special thing is a limit on the computational complexity, requiring solutions with a model size limit of 500 kilobytes. This is clearly a simplification of what the actual requirements are for applications running on real devices, but let's just say that this allowed us to create some sort of a universal measurement across the different solutions. We do welcome ideas on how to do this better, so if you have some suggestions, do not hesitate to drop us an email. So the task received a good number of submissions, and for the first time ever, it was very balanced between the subtasks. Just for a very quick reference, most systems outperformed the baseline in subtask A, but then in subtask B, there were more systems which had slightly lower performance. However, the top accuracies, they are very high. So you can see it's over 76% in the mismatch conditions and then 96% for the 3-class problem. Something about the results for subtask A. So the subtask A has received a very nice collection of deep learning methods and algorithms, and there were many different ways for dealing with the device mismatch. So you can see that the top systems have very good generalization properties. The accuracy on the seen and unseen devices doesn't have a very large gap between them. So a large majority of these systems use the data augmentation, and then some of them used also more specific methods for dealing with the device mismatch, things like domain adaptation and spectrum correction. So overall, this resulted in a very highly competitive performance. Subtask B had amazing participation. So here the classification problem was not the most difficult, but the focus was on the model size. This figure has the accuracy versus parameter count, which is not completely fair because there's not really parameter count that we measured, but most of the solutions were based on quantization of the parameters in order to comply with the size limit. And also most of them were just below the size limit using 16-bit representation. So More special things were, for example, that the top rank used both quantization and pruning. And one very particular solution, the McDonald's system, which you see up there in the corner, had used a single bit per weight. So it represented weights as a +1 and a -1, which allowed it to have like 3 million parameters, while the average for the other systems is more like 600,000. So just as a very short summary of the task, I will say that ensemble methods and mel energies are still the favorite, but ensembles are used in a quite targeted way. So subnetworks are using the compositions of the spectrum or different decision mechanisms and so on. Subtask A results show that it's already possible to get excellent generalization properties over various devices, given that we have only small amounts of training data or even no training data from some of them. And this seems to point to the data augmentation as the main mechanism for these generalization properties. Then we are extremely happy that subtask B generated so much interest, because of course we know that computational complexity is an issue in the real implementations. So even though for now the solutions were somewhat limited, we hope that this will spark some continuing research into the problem. Thank you.